spot, and actually I'll go ahead and turn off the overhead as well, just to make it a little nicer. So this is basically the spot that's coming out the end of our laser here. What I have is a set of slits. What I want to do is I want to send this beam through a set of slits, as it now is doing. And you see what the result is. It's not just one spot anymore. In fact, there's a series of bright spots and, for lack of a better description, dark fringes between the bright spots. And probably from where you're sitting, you can't see this good a detail, but there's actually even some dimmer and brighter spots within these bright and dark spots. So I am currently sending it through. I'm going to use this thing as a flashlight so I can read the parameters. And let's see. Currently I'm sending it through a double slit. And the double slit has a particular slit width and a particular slit spacing. These distances are in millimeters. The slit width, we'll call it A, is given right now as 0.08 millimeters. And the slit spacing is 0.25 millimeters. That means that what the beam is passing through is a pair of holes that are like this. And each one of these holes has a width of 0.08 millimeters. And the distance between the two holes is 0.25 millimeters. And what I want to do is I want to move it, because I have other hole sizes and spacings. I want to move it so that this hole gets larger, but the spacing stays the same. So we're going to move it to, we're going to make the hole smaller, 0.04 millimeters. What do you expect to see happen on this screen when I do that? What do you expect this pattern to do if I make the holes smaller? Think about that while I adjust the holes. And there it is. So I just made the hole size smaller, but the spacing is the same. What do we see? What difference?
Smaller.
What got smaller?
The length of how spread out.
Like this length, or like between one bright one and the next bright one?
Yeah.
Got smaller? Okay, let's, for comparison's sake, there's the larger hole size, there's the smaller hole size. Larger, smaller. Larger, smaller. So do we agree that they got more spread out between consecutive bright spots here? I don't think they did. I think the bright spots are about the same distance apart. However, and you may not see this from where you're sitting, this right here, this is not one bright spot, this is several bright spots. fact, I count, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's how many I count in there, bright spots. But if you're sitting in the back, it may look like one bright, continuous fringe. And even on the camera, it may show up to be one bright, continuous fringe. In fact, I don't know if I took a photo of this to post in the video, whether it would show up or not. Yeah, this should show up. If it flashes, it may not. I'll take a little picture of it because I can post the picture in the video that we put online, in case you don't believe me that there's multiple. And I'll do the same with the other setting, which is this one. There we are. Hearing is, we have a center to where our vision is. So I didn't change the slit spacing. This is the same old original slit spacing. And if I change the slit spacing, there's the one where we have a smaller slit and same spacing. I'll try to post these pictures on there in case the camera isn't catching them very well. The other thing that I can change, by the way, let's pull up the flashlight so we can see it again. The other thing that I can change is that instead of changing the width of each slit, I can change how far apart they are. I'm given the option of changing it from 0.25 to 0.5. So let's do A equals 0.04, but now D is 0.5. And let's see what difference we get there. So that would be this right here. So what do you see with this right here? Can anybody make it out? And again, for the people in the back, I'll try to take a nice picture. What's different about this versus the other one? So 0.25 slit spacing, 0.5 slit spacing. Do we see any difference? Can't see it from back even where you're at. Basically, the difference is, if you were up close, that you'd see is that you'd see there are now more bright fringes along here, or fewer bright fringes along here, as I switch it between one and the other. All right. Now let's try one other thing, which is instead of using the double slit, we'll use a single slit. This one should be a little easier to see, other than that I have to see it. All right, so now it's only one slit, not two. And for contrast, I'll take a picture of that to post with the online video. And now I'll change the slit width. Let's get the camera, let's get the light on so I can see. So right now it's at 0.04 is your slit width, and I will double it to 0.08. And let's see what the contrast is. See that difference? So here's 0.04, 0.08, 0.16. Do we see a difference there, I hope? It seems that the larger that I make the slit opening, the thinner that each of these bright segments ends up being. So here we have some nice thin bright segments, and if I switch it like this, we basically just get a really bright long line, and you probably can't see beyond there, but there's some additional small fringes that appear here. So this is narrow opening. This is the wide opening. All right. And the same trick works with the red laser. In fact, the main difference that you'll notice is that the size of the stripes changes a little bit. So there it is with the red laser. That's the widest opening. And here's the narrowest opening. All right. There are other openings available on this aperture. I'm not really going to go into much detail with them, but if you change the shape of the opening from a pair of slits into something else, you might get a different shape of pattern coming through. This one makes kind of like a slanted cross or an X or something like that. Here's a circular aperture. It looks like an eye staring back at you now. And so on. So what we want to do if the next couple times, you can hit the lights, what we want to do if the next couple times here is look at what's happening with the pair of slits, with the single slit, etc. What are these properties called? And basically, the two things that we're looking at are what are called diffraction and interference. So with the pair of slits like this, the main thing we're looking at is what's called double slit interference pattern. But each single slit individually also gives us a pattern. It's called the diffraction pattern. And these things combined, the double slit in particular, is actually named the Young's double slit experiment, because Thomas Young did this experiment actually with sunlight, saw the interference pattern, and drew the conclusion that light must be a wave, because it turns out that this effect of interfering is a property of waves. So this finally gave us or seemingly gave us the final explanation between the argument between Newton and Huygens. Is light a particle or is it a wave? So this experiment suggests it must be a wave, because waves do this, particles do not. Particles should go through one slit or the other, and if there's only one slit, they should just pass through the slit and be done. We've already looked in geometric optics at the bending of light. We called it refraction, and that's what happened when light bent as it passes through a particular interface between one medium and another. Diffraction is another type of bending of light or other waves, But this is bending as it goes around a corner, or goes through an aperture, or goes around a sharp object. Essentially, looking at this from a top view for a single slit, you have light which is able to travel towards the slit in waves like this. And then when it hits the slit, most of this gets blocked off by the fact that there's sort of an actual barrier present. And so then what comes through is essentially a source that looks like this initially. Well, Huygens' principle says that this should act like one or more point emitters, each of which emits a wave that has sort of like a cylindrical or spherical shaped wavefront. If it's a point, it should be a spherical shaped wavefront. And so you end up with a pair of wavefronts that propagate outward from this point, or maybe a series of wavefronts, or maybe only one wavefront. Each wavefront is allowed to interfere with other wavefronts that exist in the same point at the same time. This is like having, for example, water in a tub or a pool, and you can take like a floaty toy and put it in the middle and bounce up and down on it, and that makes nice waves that radiate outward from it. So you have your single source, the waves radiate outward from the source. So it's like if you're standing here, maybe the water's really high. If you're standing here, the water's really low, and so on. And then if you keep standing here, the water's high, lowers, and then raises, and lowers, and raises. But if you have two of these things, so the second person is also doing this. The waves sort of collide with each other in your pool. And where they collide, they might make an extra big wave. So for example, maybe the regular waves come to here on you, but where they collide, they actually submerge you. Or they can make an extra shallow wave. They can collide, and now the water is like down below your pant line or your swimsuit line. The same kind of thing is happening with light here, except for that instead of having deep water and shallow water, you're getting bright spots and dark spots. So where you get a dark spot, that's equivalent to where the waves make a very shallow part in the water. Where you get a bright spot, it's equivalent to where you get an extra high part in the water. Now, with a single slit like this, the width of the slit effectively determines how many of these things are there, how many people are in the pool jumping up and down on their flotation devices at the same time. If you have a slit that is one wavelength across, so a very narrow slit, it's like having only one person jumping up and down. And the end result is that your waves will just look like this as they propagate away from it. And so what you'll end up getting is, essentially, if you put a screen here to look at, you'll get a relatively bright part here, and then it gets dimmer as you move away from this part because you have a greater distance to travel from here to here than you do from here to here. That's just drawing straight lines and seeing how long is the line. The longer the line is, the lower the intensity, and thus the dimmer the light. If you have a slit that is 2 wavelengths wide, it's now like having 2 of these guys in here jumping up and down. So now you get interference patterns, means you have a bright spot somewhere, then you have an actual dim spot somewhere, and then you might have another bright spot off at infinity. You don't get to see the one that's at infinity. If it is 3 wide, it's like adding another one of these. and so on. For each additional wavelength, it's like adding one more person on a pool toy jumping up and down. You get more and more, as a result, bright and dark spots in here. So this slit that I just was demoing, I wrote down some possible slit widths, 0.25 millimeters and 0.50 millimeters. So how many wavelengths worth of light is that? Well, it depends. Which light are we talking about? I brought two lasers to class. This one, the green one, says 532 nanometer length. This one, the red one, says 650 nanometers. So how many times as big as this are these slits? Well, we could take, for example, this one right here, the 0.08 millimeter one. So A equals 0.08 millimeters. How many nanometers is that? Anybody remember what the conversion factor from nanometer to meter is? 10 to the 9, yeah. One of these is 10 to the minus 9 of these, so I'll put 10 to the 9 here. We'll go to 1 meter. And how many millimeters? 10 to the 3. Right, so how many nanometers are there in each 1 millimeter? That's 10 to the 9 divided by 10 to the 3, which is 10 to the 6. That's 1,000,000. Okay, so this thing right here, if you do the math, is 80,000 nanometers. So how many times each of these is it? Well, now is calculator work. So we pull the calculator out, plug it in. $80,000 divided by 532. So there's 150. This width is 150 times as big as the green. 150.37 something or other. Okay, so this is like having 150 people lined up in the pool on their little pool toys, jumping up and down at the same time. And for this one right here, for red, 80,000 divided by 650 gives me 123. 0.07 something. So for the red light, it's like having 123 people lined up in the pool like this, jumping up and down on their pool toys. It also tells us, therefore, how many total bright and dark fringes should we be able to see. It turns out that it is, the relationship has to do with a sine function. Here, by the way, is a nice image of what happens if you go large hole versus small hole. And this is, again, using presumably water that they've shone a light on to illuminate the waves. So here's for a large hole. You do get a little bit of diffraction, but not much. For a small hole, you get something like what I've drawn here. It turns out that the larger your hole width is, the greater number of bright and dark dark spots you should be able to count. And therefore also the smaller each individual bright and dark spot has to be, because ultimately it has to fit in some finite region of space. Conversely, the longer your wavelength, this is long wavelength, this is short wavelength, the fewer bright and dark fringes there are. To the point where if A and lambda are equal, you no longer get bright and dark fringes, you just get a single wave output. Okay. The upshot of this is that if you take something with very long wavelength, like a radio wave, and here are some rough estimates for how large a radio wave is. Radio waves diffract very readily around just about anything. There's not a lot of interference if you put, for example, a building in the way that somehow absorbs radios. And that's if you find one that actually absorbs radios. Obviously, we get some radio waves through the building because you can put the radio in here, turn it on, and listen to it. If you have a very short wavelength, then you get a lot of interference anytime that you have something you have to go around. So where does the interference come from? It comes from what's called the principle of superposition. That's basically what I've tried to illustrate here with the pool analogy. If you want to figure out how high a wave should be that's been produced by a pair of people jumping up and down on their pool toys in the pool, you do that by figuring out how high a wave is for one person jumping up and down. Then you figure it out for the other person jumping up and down. And then you look at a particular location in space and say, how big should this wave be at this location of space for each of these people, and you add them together. That's superposition. Now, recall that a wave also is traveling in time. So it's not just varying in space, but also in time. So if you go and do this in the pool, if you stand somewhere in the pool, you will notice that the wave gets really high and then the wave gets really low on you. So at some point you're almost all out of the water, and then at some point the water is up over your head. And when the two guys stop jumping up and down, maybe the water levels out to your chest level. With light, the same thing is happening, but it's happening so quickly that in the bright areas, it does still go to a high and then to a low of 0, but it's so quick that we don't notice it going to highs and lows. And one demonstration of that is the fact that I began with just the laser, and I pointed just the laser at the screen, and we could all just see a laser spot. It didn't look like it was flashing on and off, because it was going too quickly to see the fact that it is in fact sort of flashing on and off. If you get a pulsed laser means it actually shoots out light and then it stops shooting out light with a controllable time to it, say 10 times a second. You'll actually notice it flashing on and off. These lasers, it happens 10 to the 14 times in a second. That's way too fast for your eye to notice it. So a bright spot just means a spot in which you get some variation from dark to light over some amount of time. Dark spot, it turns out, for a fixed distance, is a location where the analogy to this pool would be if you stand there, all the water is gone from that location in the pool. Can you make that actually happen in a pool? Maybe. You'd have to have somebody being pretty wild on their little pool toys. But you might, with just the right frequency, be able to get a standing wave where there's zero water in some locations of the pool. Or maybe just a continual shallow point. Might not be zero water, but might be very little water. Here it's actually like having zero water. So in other words, you stand in that part and you get dry. If you look at that part, you see dark. Okay, the difference between these two is what's called the difference between constructive and destructive interference. So constructive interference in terms of light is where you get the brightest spot. In terms of the pool, it's where you have the deepest wave. In terms of sound, it would be where you hear the loudest noise if you have a pair or set of speakers. Did you know that you can hear different noise levels with a speaker if you put out a single frequency? I didn't bring the speaker here because you'd have to kind of move around a bit to find them. But if you take a pair of speakers, you set them up and you tell them to play only one particular frequency, then you can walk around the room and there will be parts in the room where you can stand and you will not hear the sound coming out of the speakers. Most of the rest of the room, it'll be shrill and loud and annoying. Skip a couple of those. So where diffraction interference comes from. You have light that's bent around this corner. Effectively, that's like having multiple sources. And what you do is you figure out how far does it have to travel from each source to get to a particular location on the screen. How far does it have to travel to get from each source to a particular location on the screen? And what you do is how far it travels tells you, A, how intense should it be from that source, but also B, how do the sources line up relative to each other? It's sort of like if you have a couple of pulses traveling on a string, how they line up relative to each other determines what the string will look like at that moment in time. So here you have two where both ends of the string are sort of shook in the same direction to make the pulse. So you get a pulse that's up and a pulse that's up. And when they collide, it makes a really tall pulse, and then they pass through each other. Here you have them shook as if one is up and one is down, and where they collide, the string just sits. It's at equilibrium. There's no pulse. The same thing is happening optically here. What does a light beam look like from each source? Well, it looks like a sine wave, like this. So you have one sine wave like this. Then you have another sine wave which may be like this. In other words, they're in phase with each other. The peaks line up, the troughs line up. And the resulting sine wave that you get from interfering these two will look like this. So it just looks like a taller version of the individual ones. All right. You can also have them arrive out of phase with each other. Out of phase means they arrive looking something like this. All right, when you add these two together, peak and trough gives you 0, trough and peak gives you 0, etc. You get something like this. This is what happens when you get a dark spot. The other one is where you get the brightest part of the bright spot. So it turns out that depending upon where on the screen you're looking, determines whether these line up like this or the other way, or somewhere in between. To figure out which way is which, you have to use sines and cosines a bit. By the way, I have here, although it seems to have cut a little bit, I have here one picture of diffraction through a single slit that was taken by exposure long time to a camera. You see, there are, what it actually says, I don't know why it's been cut out like this, but it says max and min. The maxes are where you have a bright area, the mins are where you have a dark area. And they've been placed, and you'll notice that the spacing is the same between maxes and mins, with one exception, which is the middle maximum is always a bit wider than the others. So the equation which tells us where the dark fringes are looks like this. A sine of theta is m times lambda. So what do the terms in this equation mean? A, again, is how wide is your slit. Lambda is what is your wavelength. So this ratio, or this thing that I've written down here, A equals 150 lambda, A equals 123 lambda, that's sort of like if I divided A by lambda, what is m giving us? M times sine of theta somehow. And the reason why we care about how many times is lambda is because sine of theta has a maximum possible value. What is the maximum possible value of sine of theta? We actually did this a few days ago when we were talking about refraction. What happens if you're trying to take an arc sine to figure out what the angle is? What happens if you take the arc sine of, say, 0? Well, you can put it in your calculator, and your calculator will spit out that the answer is 0. So sine of 0 degrees gives you 0. The arc sine of 1 gives you 90 degrees. So if somehow sine of theta is equal to m lambda over a, and m lambda over a is equal to 1, and it's telling you that theta is 90 degrees. That's basically like going at here's 0 degrees, at a 90 degree angle from the slit. Where does that point exist? Well, basically it's going to be on this wall somewhere, like the ceiling or the wall perpendicular to the slit. Or if you don't have walls, then you need to have an infinitely long screen to see it. So you don't see it on the normal screen. What happens if you take the arc sine of 1.2? What do you get? Arc sine of 1.2. That's sine inverse of 1.2. Remember what the result of that is? Doesn't exist. It's not a number. Your calculator gives you some sort of error message. Because the maximum possible value of a sine is 1. Okay? What this is telling us is, m, what it represents is how many bright fringes. It's called the order. Or actually, properly, it's how many dark fringes for this thing. So m actually runs from 1 out to some maximum value, and that maximum value is determined by that if sine of theta ever goes over 1, then it's non-existent. So it's the maximum number m such that m times lambda over a is less than or equal to 1. And that's how many bright fringes, or how many dark fringes you get to have above. And now multiply it by 2, because you can also go below. That's how many total dark fringes you can have. And hence, also how many bright fringes you can have. Another thing to notice on this equation, it predicts all the things that we saw in the demo this morning for us. Okay, first thing that we saw was what happens if I change slit. Okay, it doesn't predict anything with slit spacing, but slit width. If I double the slit width, what happens to the number of fringes? I need to plug it in and show it again. Very dim. You might have to turn off the lights to see it. There it is. Okay, so let's make the slit get progressively wider. So I just doubled the slit. I doubled it again. And I doubled it again. What do we see? The wider the slit is, the more fringes we see, right? There's not very many fringes here. There's more here, for example. Okay. The equation that's up there predicts that. All I have to do is rearrange the equation. Basically, sine of theta is m lambda over a, or in other words, m maximum, the maximum order and hence the maximum number of fringes that I see, has to be, m has to be sine of theta times a over lambda. But if I want the maximum number, I have to put the maximum number here. That's 1. And so the order maximum just becomes a over lambda. Well, we calculated what a over lambda was here. It's 150 for green. Right? For the particular slit width of 0.08, which is actually, I think the one that it's on right now. Now, do you actually see 150 of these? Well, no, because they get progressively dimmer as you get away from the center. It gets too dim for you to really see. But if we had a bright enough laser, you could. Or if you had a photon counter, you could. And again, it's not 150, it's 150 times 2 dark fringes, or 150 times 2 plus 1 bright fringes. All right, now if I make the slit get narrower, that's basically equivalent to making A get smaller. So here is A is equal to 0.08. Here is A is equal to 0.04. Sure enough, I have fewer fringes here. Does the equation predict that? Well, yes. If I make this number smaller, then that makes this number smaller as well. Fewer fringes, etc. Well, I think we're out of time for today's class.